Hello, everyone. My name is Corbin Zapp, and this is my final research presentation for LSTM-based satellite trajectory prediction for space traffic management, or in shorter terms, a data fusion system for space traffic management using artificial intelligence. In this presentation, I will walk through the methodology, implementation, and results of using AI to improve satellite tracking and space situational awareness. Let's get into it. First, what is the importance of it? Why am I even worried about this? Why am I talking about it? Well, with the growing number of satellites in Earth's orbit, space congestion has become a serious issue. Traditional physics-based models, which is what we use now, uh, while they are accurate, they are very, very slow for real-time variations caused by maybe atmospheric drag, gravitational perturbations, any type of external force. And this research explores how deep learning, specifically the long short-term memory, the LSTM, networks can enhance space object tracking and prediction accuracy. So my goal is to improve space traffic management using AI-driven trajectory forecasting. And the problem, as I stated before, why am I talking about it? It has to do with the congestion in space. So the primary problem that we face right now is space tracking is predicting satellite accurate is predicting satellites accurately. Now, they are very far away, moving very quickly over 17,500 miles per hour. What happens when something that fast, that's not very sturdy, hits something else moving also that fast? It's going to explode. It's going to be debris everywhere. It's just going to be floating around in space. Uh, The Kessler syndrome, which is referring to this, it actually describes that growing risk of collisions, where debris from past collisions causes a chain reaction, making space travel and satellite operations way, way more risky. Now, current tracking methods do not adapt dynamically like an AI system or a machine learning system would. We have to have a guy here on the ground, and he has like a controller, like an Xbox controller, maybe some type of computer controller, and he is checking through other satellite data and telemetry, which is just in quick terms, it's shooting a radar, hitting the satellite, and then going down to another radar like a triangle, and then judging where it's at due to those 2 points. And that is how right now we are judging where a satellite is because we do not have an AI-based system in the industry right now at all in orbit anywhere. So because they don't adopt or adapt dynamically, this leads to huge problems if there was debris. And as you can see on the PowerPoint slide here, you'll see that these arrows, these vectors, are going from satellite launches to inactive to fragmentations, active satellites, and disabling satellites. And then you'll see the medium, large debris, the small debris. You'll see all this here. And it's just showing the Kessler syndrome of how gravity is affecting how this debris will fly and where we need to be with our satellites and what we need to do with them and how that will affect it. That it inevitably with space debris will hit our objects in space that we definitely need up there for a whole bunch of reasons. Okay. Now, what you're seeing here at the bottom of the screen is called a TLE. This is a two-line element. Now, for this research, this is essentially the only data document I worked with. It was the only document for data I worked with because this is how you get satellite data. Uh, this is where celestrak.org, this is where I went and got this. I had to request it because they only gave me a little bit and I had emailed the guy and he got back to me in 2 days. That was awesome. And I got a bigger document with all of it was just a text file with all of these 30 days of the last active satellites over the last 30 days. Sorry about that. And it has all their positions. And that's what I was testing my LSTM model on. So another thing is that these TLEs, what they contain is orbital parameters. That's for the active satellites. Now, they were converted to Earth-centered Earth fixed, which is ECEF coordinates, using the SGP4 propagator, which is the that is embedded into Python to get mock real satellite data to use for mock space traffic management systems like myself or any other type of science that somebody want to conduct or experiment. So this ensures that the data, the SGP4 propagating the ECEF, that ensures the data is structured correctly for machine learning. Now, let's go ahead and look at that, how it looks in the code. Let me go ahead and pull that up. Okay. Uh, Perfect. So as you can see here, we have the reading in the TLE data. The gp.text is the file where all of these last or the active satellites in the past 30 days positions are. And as you can see, it read in random number of 50 samples each time. And that was so I didn't want it to just go down the list and then LSTM model be able to predict or to memorize, which did happen, and I'll get into that. But let's keep going. So then opening it up, putting it in, showing how to read it, that because there's two lines. And this is just, standard. There's even like a whole page for that. This is always getting a fresh random subset of 50 different of the two-line element documents. And then this is getting the position and the velocity of the TLE data. And that's calculating that. And then we're creating the benchmark from the TLE file. You'll see here, whoops. Start times, delta, all its positions, its average positions, and then we'll get into the LSTM next. But all this right here had to do with reading in TLE data. That was something I had to learn to be able to do this project. Okay, perfect. All right, so the LSTM model. Uh, Now, why is this useful for sequential space tracking? So they're ideal for that, for sequential space tracking, because they handle time series dependencies. Now, it sounds like a lot of word salad, but what that means is the model takes in 10 past time steps or past locations of the satellite, and then it predicts the next XYZ coordinates based off of that. XYZ coordinates meaning where it's located on the globe in a 3D plane. Now, it consists of two of these LS2M layers with 128 units, dropout layers to prevent overfitting, and a dense output layer. The loss function is mean squared error, or MSE, and the optimizer is Atom, and it helps optimize learning. Now, let's go ahead and go back to the code so I can show you that a little bit. But before we do that, I'm getting ahead of myself. The input layer, see the 10 pass, and then you see the dropout layers 28% to prevent overfitting. And the dense output layer is what predicts the next XYZ coordinates. And the Atom with the dynamic learning rate scheduling. The Atom optimizer allows the scheduling. Switch back over to the code. Okay. So right here, we can see that we're talking about the LSTM, or once again, if you forgot, the long short-term memory network. And so here's the time steps going back. So if I change this to 20, it would go back to the last 20 points and so on and so forth. And then the dropout layers, and then the dense layers. So we know that it's XYZ, right? And the dropout layers prevent overfitting. And right here is where we get into the scheduling. And this is when the training, but you can see here that the optimizer's Atom and the loss is MSE. So the loss or the Euclidean distance is based off the mean squared error, which I guess is the Euclidean distance. So anything I missed in the LSTM? No. Perfect. Okay. So for the model training, the optimization, uh, it was trained using the sliding window approach, and where sequences of 10 past positions, so the past 10 time steps, were used to predict the next step. That's what we were saying. See if I can go back. The 10 past time steps, that's what this is. And what this is you should look at it as an array. So the 20, the 10, and the 30, all those can be summed up to make 60. And that's in a three window. But you can slide that window one element over. So now the 20 is out, but the 40 is in. So you could say that the sum is 70. Or sorry, 80. But that is how the sliding window works. And then the noise injection, which we should just go ahead and go back to the code here. The noise injection, where am I at? Sorry, where? Oh, sorry, right here. This is where the noise injection was added. And now, what is this? This was you add noise to noise up the data to not make it perfect. Because remember earlier I said we had issues of memorizing. My LSTM started to memorize these points because they had seen them before. So noise injection is used to prevent overfitting. So it ensures that the model learns the general orbital behaviors rather than just memorizing the patterns. So like a good way to put it is they didn't just cram and study right before the test to memorize the answers. They actually, we wanted to learn the material so we can take the test at any point in time. Because once again, space is very dangerous. So we never know what's going to happen there. Okay. And we're going to go ahead and just run it here, just so you can see how it runs and trains itself in real time. We have to, whoops. Okay. So we're starting the training here, and you can see it did 100 epochs. Here's the how long it takes to do the step. Okay. Here is the loss or the MSE. And the lower this number, the more accurate that prediction was, right? That's the less far it is away from the actual point. So we want this predicted point to be as close to the real point from the satellite data as possible. And as you can see, the learning rate stays constant at 0.001 until right here where it learns on itself at epoch 24, and it reduces the learning rate by a magnitude, which is amazing. And you can see how our loss is pretty low. We started at 0.18. We're already down to 0.002. And the learning rate will stay until the next one where you see 5 to the negative fourth, which pretty good. And once again, uh, or sorry, I might not have said this yet, but there is some drop off and then it comes back. So you can see that this is lower than up here, but then it comes back stronger after a second learn or a third learn. And then it does it again. Whoops. And again, and again, and another one, and again, down to here to where we're at 6.1 to the negative eighth and a 0.0024. So these looks like our lowest might have been a 0.0017, but each time it learns, it typically gets better, as you can see in the learning rate, which is very important. Now, this did not show anything right now because I'll run it again. It was because the satellite data that pooled was on the other side of the world. Uh, the next part of this project for the next class, I am going to be making it a 3D model that you can interact with, but it was just too difficult in the time frame we had to get that functioning. I did try though. So let's look again. And once again, it starts out pretty high, but learning rates are the same, but we're getting pretty low on this. And you see it's creeping around. I'll do it one more time. If not, I'll continue on because we'll come back to code. Yep. See? So now they're coming over here, South America, and you can see that they're pretty accurate, but they're a little off, meaning that they're not memorizing, but they're pretty close. And if you're wondering why they look like that, it's not just a bunch of sporadic dots. That's just satellites typically travel in a train like that, like train cars. Okay, let's go back. Okay. Sorry. Just looking at my notes, make sure everything's good. So, for validation, prediction, and accuracy, to validate the model, predictions were compared against real satellite positions, like I was just explaining, and the Euclidean distance was what was used to measure that accuracy. So the smaller value indicates a better prediction alignment. As you can see on these two photos in the PowerPoint, the blue, which are plus signs, as you can see in the legend, the pictures are a little small. The blue is the real data that was randomly pulled from the gp.txt file or the TLE data. And the orange is what the LSTM predicted. So as you can see, the top one here, or the top left of the two pictures was around 40, I think, runs, 40 or it wasn't quite 50. 50, there was a jump, 60, there was a significant jump, and then I decided to let it ride out, and I did it up until 100. And by 100, we get the bottom right, where very vividly you can see that they're tracking. They're a little behind, but they're tracking. Now I'm at about 200 when we run it going back, which is why it might have looked a little better there, but just wanted to mention that. So the results from this, though, do get logged into a file. And I had that do that so I could determine if it really was learning on itself. I wanted to see the error. I had to know. And so do this. We'll run it here one more time. I don't know. I wish it would just always stay disabled, but with learning and learning, I haven't gotten below to the negative ace. So I'm looking for that. So we can't see it here. Actually, I want to run it again. I it hasn't done it this many times in a row in a while. That's fine. We can go to the data. So we pull up tracking results. And as you can see here, the top is 438. I would like you to remember that. And because it keeps going down, 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 by 400, it gets low here. Sometimes it goes back up, not all the time, but as you can see right here, it's looking good down to 263. So we had 438 to 263. And if we run it again, perfect. Now let's pull it back up. All right. So you can see that it started at a 247 now, where it was 438 before, just learning off of itself now. And it gets lower, lower. I was hoping I could see, yeah. So it's down to 24 here, 23, but then it goes back up. And we're back up to 27, and then it goes back here. So this is where high altitudes are causing problems. And that's noticeable because the lower we get, the the easier it is to read. Okay. And let's go back to the slides. So for the results and sorry about that. For the results and the error trends, the top the top graph here is after 50 runs, like I said. earlier, the 50 and the 100 are my marks. So top is 50 runs of the code, and the bottom is 100 exactly. And clearly, you can see that there is a much stronger spatial clustering over time. The model's been performance improved significantly over these multiple runs, and especially once we got closer to 100, even now closer to 200. At the beginning, you can see that it was over 320, which is measured in kilometers. That's what the Euclidean distance was based off of. But then, like I said, after 100 cycles of running the code, it dropped below 200 kilometers. And this is a great visualization of how well it is just learning in just 50. And for the next one that I'll be doing, I'm going to try to make those numbers a little bit farther apart. Once again, the code's running quickly now that it's Sunday, but it hasn't always been running quickly. It's very data intensive. So now let's actually go back to the code to where, no, not yet. Sorry. Let's talk about the comparison first. So I'm getting ahead of myself, apologize. But you want to compare the SGP4, which is the highly accurate uh it's the highly accurate model based off of real physics of real data of satellites. So it can't do any predicting and it's not dynamic. And but it is very highly accurate for short-term predictions. Uh, but it relies on these predefined orbital mechanics. Like I said, it's defined physical, um, just physical measurements, right? There's no prediction involved. It's if it's there, it will read it. But that's, like I said, the complete opposite of the LSTM, which is learning from past data and improving on that data over time, as we saw in the last the last graph here, which is why this is important. It's not going to be great now, but it'll be better soon. And we need to get it started now so it can learn. Uh, and that's why it's so promising. In AI, I just cannot believe it's not in the industry yet. I've said it multiple times, but the space industry is probably the industry the most that is lacking in the AI department. And I'm very interested to see where it goes. Okay. Sort of the challenges. Um, we have limitations of data constraints as civilians. Uh, I do not have any clearances. I do not work for the government. I don't work for Lockheed Martin. And that is, it's kind of annoying because you can only get two satellite data readings two times a day within 2 hours. If you do it, you get banned for the couple hours. And then if you try to do it one more time, it's 4 hours and you can just never get the data. You just cannot get real satellite data because it's a security risk. So you have to wait until the old data comes out. And but by doing that, it's not tracking it. And it's a huge problem for everybody working on this. And there's not just me, there's a bunch of people in the industry now trying to come up with a solution to this. But when no countries want to let their satellites data roam and be accessible to just an average civilian like myself, it makes it very difficult to actually judge if it's like you're always at practice for a sport, but you never actually get to play the game. And that's not good. You playing the everything's different during the game. On top of that, uh, the variability of the orbital altitudes and the different types of orbit it had caused the problem. That is what's causing that dip to go down real low. It's looking good, and then it pops right back up in the tracking results. Um, and from personally, in my opinion, because I think it's going to be so good for space situational awareness or just knowing where other objects are um, in the vicinity of yourself, of the object itself. So like a satellite knowing where other things are in orbit. I think we're going to have some type of hybrid where it'll be a system that alerts us. For this is in the near future. It'll change the full AI soon or later on, but I believe that it'll alert us. Right now, we don't have that. and then we will be manually on the ground, being able to probably send it codes or commands that are a little bit better than what we have now. I imagine that will come first before a full functioning AI data fusion system. And I wanted to go back to the code now and just make sure that we or you have seen everything. And I wanted to touch on one more part of the code. Where Oh, sorry. I had actually already, I wanted to talk about the scheduling and epoch and batch size, but I already did that. So perfect. So we'll just run the code one more time here for you because it looks like it's getting close to midnight, and this took me right up until Sunday. Happy I got it done though. All right, so one last scroll here, 0.39. Good. Still only to the seventh. And as you can see, it's not the best. And we can see that one more time to the tracking. Wow, the error is actually low, but it went back up. So it's not perfect yet, but I do like where it's at. Okay. And so for conclusion, I think that the LSTM model offers a very effective solution for improving space object tracking. Not just AI in general, but specifically this model network. I believe it is honestly perfect for it. So over multiple runs, as you saw, the prediction accuracy improved significantly, making it AI-driven approaches even more valuable for collision avoidance and space traffic control. Future research will absolutely focus on refining and generalization and efficiency of AI and machine learning for these satellites. And I did I miss? Good. And for acknowledgement, I want to thank Celestrack for giving me access to the TLE data of the last 30-day active satellites. Like I said, even the old data is tough to get, but they got back very quickly with me. I was very appreciative of that. You can email me at my email there, cjzap at student.fullsail.edu. And I also wanted to thank Professor for all my messages to him. Thank you, because I didn't think I was going to get it in by tonight. Very excited. I'm happy where we're at. And thank you for a great class, for the second class I've had with you. And I hope everybody has a great week.